Hello, welcome to my video on polynomial division. So before I divide polynomials, just a quick reminder of some division vocabulary. When we divide numbers or polynomials or expression, anytime we divide, the thing we are dividing is called the dividend. We divide our dividend by what's called the divisor. After we've divided, the result is the quotient. So the quotient is all of the values that go evenly into the dividend. The quotient plus the remainder. And our remainder we can express as a fraction by putting it over the divisor. So as a quick pure numerical example, if I am dividing 20, let's say I'm dividing 40 by 3, 40 would be my dividend, 3 would be my divisor. 3 goes into 4 one time. Then I could say, okay, subtract the 3. If it goes into 4 one time, I have 10 left. 3 goes into 10 3 times. Then I have 9 left. At that point, I have 1 left over. 3 does not go into 1, so 1 would be my remainder. And I could say 40 divided by 3 is 13. 13 would be my quotient, plus my remainder of 1 over my divisor of 3. So our dividend is what we are dividing. Our divisor is what we divide by. That gives us our quotient. Our quotient is how many times the divisor goes into the dividend evenly. And then if there is leftover, that's our remainder, which we can express as a fraction of the divisor. So let's apply that to polynomials. I'm going to do each of these in two ways, two different visuals. I'll do polynomial long division, then I'll also show this with the box method. And then at the end of this video, I will demonstrate something called synthetic division, which is a kind of shorthand that some people enjoy. So first, I will do this problem with traditional long division. So if I have 4x cubed plus x squared minus 4x plus 5, I'm dividing this by my dividend of x minus 2. So if I'm going to write this out using the long division algorithm, I put my dividend inside, I put my divisor outside, and I'm going to focus on my leading terms at all times. So first, 4x cubed divided by x gives me 4x squared. So this came from 4x cubed divided by x. That gives me 4x squared. That means x minus 2x goes into 4x cubed, 4x squared times. But now I want to see how much is left over from the rest of the terms. So 4x squared times x minus 2 times x minus 2 tells me, okay, based on what I have so far, I have used up 4x cubed minus 8x squared. And what I'm going to do is I'm going to take that away from my dividend and see what I'm still left with. So when I take it away, my cubic term goes away. And then x squared minus negative 8x squared. So remember that there's a 1 here. So 1 minus negative 8 is like 1 plus 8, which gives me positive 9. So that means at this point, I still have 9x squared to deal with. I'm going to bring down my linear term and keep going and repeat this process. So now I'm going to say, okay, my 9x squared, how many times does x fit into 9x squared? It fits into that 9x times, because 9x divided by x is, or 9x squared divided by x is 9x. So that gives me how many linear terms fit in. Then once again, I'm going to figure out, okay, if I have 9x of these in here, what does that give me? So that gives me 9x times x minus 2 gives me 9x squared minus 18x. So that means this 9x squared minus 18x, that's been put into my quotient. I'm going to subtract it, see what I still have left to deal with. So -4 minus -18, that's kind of like -4 plus 18, leaves me with positive 14x. Tack on my constant term. So I've whittled my dividend down to 14x plus 5. Now I'm going to see how many times does x minus 2 fit into 14x plus 5. It fits in 14 times. Because here I have I have 14x divided by x. Sorry for that pause. If that fits in 14 times, then at this point, now I'm going to say, okay, if it fits in 14 times, let me remove that from my dividend, see how much I still have left to deal with. So I have 14x, or no, not 14x, 14. This is just 14 times. So 14x minus 28. Going to subtract that from my dividend, see what I'm still left with. So 5 minus -28, that's like 5 plus 28, leaves me with 33. At this point, x minus 2 does not go into 33 because I don't have any constant. I need at least an x term if I'm going to fit an x inside of something. So this 33, I'm going to call my remainder. So this means when I divide 4x cubed plus 1x squared minus 4x plus 5, I divide the entire thing by x minus 2. What it leaves me with is 4x squared plus 9x plus 14. That is my quotient. Plus a remainder of 33. And since there's that remainder, I'm going to say 33 over x minus 2. Because that remainder I was not able to divide any farther. So I need to express it as a fraction over the divisor. So what this means is 4x cubed plus x squared minus 4x plus 5, if I use long division, is equivalent to 4x squared. Once I've divided by x minus 2, it's equivalent to 4x squared plus 9x plus 14 plus 33 all over x minus 2. So this is visual number 1. This is using the long division algorithm. The other way you can visualize this to get the same response is you can organize it in a grid. So what I'm going to do is just going to take my dividend here. Copy it over. Then divide. Here's my second method. So for my second method, since my leading term of the dividend is third degree, that third degree x cubed tells me if I'm going to organize this in a grid that I would need to use 2 rows, because I'm dividing by a binomial, x minus 2, and 3 columns, because I need a column for x cubed, a column for x squared, a column for x, and then the lower right will be my constant. So I'm going to put my leading term right here, and then I'm going to say, okay, I'm dividing this by x minus 2. And what I'm going to do is I'm going to work my way across this grid and figure out the quotient, which will live on the top of the grid, one term at a time. So the first term I'm going to figure out is this leading term of the quotient. If I have 4x cubed and I've divided by x, my result is going to be 4x squared, right? So this begins just like the algorithm did. 4x cubed divided by x gives me 4x squared. If I have 4x squared up there, that tells me what's going to live down here. Because 4x squared multiplied by -2, 4x squared multiplied by -2 must be -8x squared. Notice that this -8x squared is playing the same role as this one did over here in the long division. So this and this, we're doing the same thing, we're just visualizing it differently. So I have negative 8x squared, which means I've begun to get my quadratic second degree terms. But in my grid layout, the only places where I can have quadratic terms are going to be in those two yellow positions. So I need my yellow positions to sum to 1x squared, because the inside of my grid should add up to the standard form of the dividend. The dividend should be the sum of all the terms inside the grid. So I need those two yellow boxes to add up to 1x squared. Right now, I have negative 8. I want negative 8 plus something to give me 1. If I want to get negative 8 plus something to give me 1, that something must be positive 9. So here I'm going to put positive 9x squared. And now you'll notice 9 minus 8 gives me, so 9 minus 8 gives me 1. So I have used this to figure out the missing quadratic piece. Now that I have this quadratic piece, I can continue with my pattern. I can use that quadratic piece to figure out what goes up here. So 9x squared divided by x tells me that the linear term of my quotient in purple is going to be 9x, because I need 9x times x to give me this box, 9x squared. And now that I know my 9x, I can figure out this by doing multiplication. 9x times negative 2 gives me negative 18x. So you can see I'm kind of like working down a box, up a diagonal, down a box, up a diagonal. So at this point, I have negative 18x. That's my first linear term. That's my first x term. The x terms are going to be in this diagonal, my two green squares. And I need those two green squares to sum to negative 4x. So I have negative 18x. I need them to have a total of negative 4x. That tells me, and I can do a one-step equation on the side if I need to, or I can check in my calculator. So careful about your negatives. But that tells me my second green box is going to need to be 14x. Notice once again, we're still getting these same values. So 9x squared, 9x squared, negative 18x, negative 18x, 14x, 14x. All the same values, we're just visualizing this differently. It's the same exact process, same math. Now, 14x divided by x, like we did here, 14x divided by x, gives us 14. So my 14 lives up here. And now I multiply 14 times negative 2. 14 times negative 2 gives me my constant of the quotient. 14 times negative 2 gives me the constant of the quotient, negative 28, down here. However, you'll notice that negative 28 is not 5. So the interior of my grid all adds up to the dividend except for the constant. The constant is where I run into an issue. I have an issue because when I do this division, I get a remainder. So if I'm using my grid method, the way I deal with a remainder is I give myself an extra box over here, but I know that any boxes outside of the grid represent my remainder because they did not fit nicely into the quotient like all of the terms inside did. So if I have negative 28, but I need my pink areas to add up to positive 5, that means I need an extra 33. Because 33 and negative 28, those add up to positive 5. So that means like if this is what I ended up as my constant, I'm going to have a remainder of 33. And now you see we have gotten the same result, but with a more kind of area model type of thinking. We divided 4x cubed plus x squared minus 4x plus 5 by x minus 2. The quotient was 4x squared plus 9x plus 14. The remainder was 33, which we put over the divisor of x minus 2. So two different methods of performing the same division. So at this point, I'm going to just do a second example with the same two methods. So down here we have 4x cubed plus x plus 6, all divided by 2x plus 1. First, and I'll do this one slightly faster since you've seen one example. I'm just going to point out some important differences as I go. So first thing that's important here, 4x cubed, you might notice that the dividend does not have an x squared term. So if you're ever missing a term, like if the exponents aren't going 3, 2, 1, 0 or 4, 3, 2, 1, 0, if you're missing a term, you want to include that term in your work as a 0. Because you want all of your places accounted for, right? So even though the problem was just written as 4x cubed plus x plus 6, I want to rewrite it as 4x cubed plus 0x squared plus x plus 6 so that I don't lose track of the place where I would usually put quadratics. Then I'm going to divide this by 2x plus 1. So I'm going to move this one a little faster. 4x cubed divided by 2x gives me 2x squared. 2x squared times 2x plus 1 gives me 4x cubed plus 2x squared. Now you see why we need to save that quadratic space for ourselves, because even though it wasn't in the dividend, it does show up in the quotient and our work. So then I'm going to subtract. 0 minus 2 gives me negative 2x squared. Bring down the positive x. So negative 2x squared divided by 2x, negative 2x squared divided by 2x, that's going to leave me with negative x. Negative x times 2x plus 1 gives me negative 2x squared minus x. I'm going to subtract that from my existing dividend. Negative 2x squared minus negative 2x squared gives me 0. X minus negative x gives me 2x. It's like 1 minus negative 1. So 1 plus 1 gives me 2. Going to bring down my plus 6. 2x divided by 2x is 1. 1 times 2x plus 1 is 2x plus 1. I'm going to subtract to see how much I have left. 6 minus 1 leaves me with a remainder of 5, which means that 4x cubed plus 6 plus x plus 6, all divided by 2x plus 1, gives me a quotient of 2x squared minus x plus 1, and a remainder of 5. My remainder of 5 I put over 2x plus 1. So there is my result expressed as a quotient plus a remainder over divisor. And now let's do the same problem using the box kind of grid method. So my leading term of my dividend is x cubed. That tells me I need 3 columns. My divisor is a binomial. That means I need 2 rows. I'm going to put my leading term right here. So 4x cubed. 4x cubed divided by 2x gives me 2x squared. 2x squared times 1 gives me 2x squared. I need, and even with this method, I'm going to kind of like rewrite. I'm going to rewrite my dividend with that 0 so that we can keep track of what we're doing here. So I have 2x squared, but I need there to be 0x squared. So if I have 2x squared, I need there to be 0x squared. I want my other box to be negative 2. Negative 2 plus 2 is 0. Then we're in business. Negative 2x squared divided by 2x gives me negative x. You see, these are all the same operations, just a different visual. Negative x times 1 is negative x. Now I need my green to add up to positive x. So right now I have a negative x. I need that to add up to positive 1x. So I'm going to have my other box be 2x. 2x minus x gives me x. So remember, these are all like, this is like negative 1. This is like positive 1. So 2 minus 1 gives me 1. Based on that, 2x divided by 2x is positive 1. 1 times 1 is positive 1. So this is my remainder. Or no, this is not my remainder. That's my constant. I need, in my dividend, I had a constant of 6. But in this work, so far I've accounted for only one of them. So that means I need 5 more. I need 5 plus 1 to give me that 6. So I have a remainder of 5, which once again gives us the same result. 2x squared minus x plus 1 plus 5 all over 2x plus 1. So we can see same problem, same result, same remainder, same quotient, but two different ways of visualizing things. All right. So key things to watch out for with division are be very careful for your negatives and be very careful for just your kind of little exponent details that happen along the way, because one small negative mistake early on can mess you up. All right. So at this point, these are the two methods of doing long division. What I'm going to do is I'm going to, at this point in the video, if you just wanted to look at long division, you can pause and that is finished. But I'm going to take both of these examples and show you how you would use them using synthetic division. So synthetic division is kind of a shortcut that some people like to do. And I'm going to show you how that would work with both of these so that you can see kind of the strengths and weaknesses of synthetic division. All right, so at this point, what I'm going to do is I'm going to show you a trick called synthetic division. Synthetic division can be very convenient if you're dividing by a binomial where it's just 1x plus or minus a constant. However, synthetic division can get a little more annoying in the second example where you have something like 2x plus 1. So synthetic division is a nice trick to know, but it becomes really inconvenient depending what you're dividing by. So that's why I'm going to show you with both of these examples. So I'll show you with the convenient version first. If we're doing synthetic division with my first example up here, this is the first problem we did. We know that the result is 4x squared plus 9x plus 14 plus 33 all over x minus 2. Synthetic division is kind of a shortcut. What I do is my first step is I have to make sure I'm dividing a polynomial by something of the form x minus a or x plus a. So I need to have a 1x in my divisor. So I do, which means I'm just going to list my coefficients in descending order. So my coefficients are 4x cubed, 1x squared, negative 4x, and 5. So I'm just going to list my coefficients atop the box. And then what I'm going to do is I'm going to say what value would make my divisor equal to 0, right? Like if this was a factor, what would be the x-intercept? So the value that would make this 0 is if x were equal to 2. So I'm going to take that 2 and I'm going to put it out front. Notice that's not a negative 2. I'm saying what value makes my divisor 0. And then I'm going to do a really kind of easy, repeatable algorithm that's going to bring me straight to my result. So my first step is I'm going to take my leading coefficient, copy it down here. Then I'm going to take that 4, I'm going to multiply it by my 2. 4 times 2 gives me 8. Then I'm going to add my 1 and my 8. 1 plus 8 gives me 9. And I'm going to repeat. 9 times 2 gives me 18. Negative 4 plus 18 gives me 14. And then 14 times 2 gives me 28. 28 plus 5 gives me 33. So what I was doing all along there is I bring this down. 4 times 2 is 8. 1 plus 8 is 9. 9 times 2, 18. Negative 4 plus 18, 14. 14 times 2 is 28. 5 plus 28 is 33. And you'll notice that I labeled the first ones in purple and the last ones in pink. That's because my final number on the bottom is my remainder. So my initial values in purple are my quotient, and I have a remainder of 33 all over x minus 2. So you can see in this example, synthetic division is a nice shortcut that gets you right to your quotient without doing like all of this that we did up here, right? So synthetic division works very well when we are dividing by something like x minus 2. Synthetic division gets more complex when we have something like 2x plus 1. Because if you don't have x, like 1x plus or minus a constant in your divisor, what you need to do first is you need to manipulate your original division problem until you are dividing by 1x. So what that would look like in this second example is I would need to multiply the numerator and denominator by 1/2. And I chose the number 1/2 because I want to turn that 2x into a 1. So I'm going to multiply this by 1/2 on the top and 1/2 on the bottom. 1/2 times the numerator, 1/2 times the denominator. I can do that because really I'm just multiplying by 1, right? 1/2 over 1/2 is 1. And so I can multiply the numerator and the denominator by the same thing. That gives me, if I distribute, 2x cubed plus 1/2 x plus 3 all over x plus 1/2. Because I also need to distribute on the bottom. So in order to do synthetic division, I first need to manipulate my problem so that I have that 1x in the divisor. Now that I have that 1x as my divisor, then I can set up my synthetic algorithm and it will work for me. I just might have some annoying fractions. So in this example, I would say I have 2x cubed. I have 0x squared. Make sure to keep that 0 placeholder. I have 1/2 x. And I have 3 as my constant. If x plus 1/2 equals 0, then x must be negative 1/2. So out here, I'm going to put negative 1/2. So synthetic division still works, but you can see now I'm going to have to do all this fraction stuff. So step 1, I'm going to bring my 2 down. 2 multiplied by 1/2 gives me negative 1. 0 minus 1 is negative 1. Negative 1 times negative 1/2 is positive 1/2. 1/2 plus 1/2 is 1. 1 times negative 1/2 is negative 1/2. 3 minus 1/2, and then this is another example of where it gets a little annoying. 3 minus 1/2 is 2.5, or 5/2, which means that in this problem, my result is 2x squared minus x plus 1 plus 5 over 2 all over x plus 1/2. And then you see I got myself this kind of like messy situation here that if I'm strong with my fractions, I can convert back, and that will be, I could multiply the top and the bottom both by 2, and that would be 5 over 2x plus 1. So synthetic division can still work if we don't have a divisor that's just a straight up x, but you can see you have to do a lot of kind of annoying fraction work before and after, and the shortcut may not be worth it so much anymore. So when you have this, synthetic can be nice, but if you want strategies that will always work, these long division strategies will always work for you, no matter what you are dividing by. Synthetic division is a shortcut if your problem is set up in a way that happens to be convenient.